Giuseppe is one of our repeat offenders as well, starting with a small talk in Barcelona, I think it was.
Yes.
I think you've been speaking at almost every SuriCon so far, and so Giuseppe has been contributing to Suricata, and today he's going to talk about maybe going to talk about his latest contribution, an SIP parser and logger.
Okay.
You should see it here if it's. Not working. Yeah. There
Nice.
it is.
Okay. Come on, sorry. Okay, hello everybody. In this talk I'm going to talk about VoIP and how we can use Suricata to detect those networks. I think that you are all tired, so for this reason I would like to start my talk with some practice. But let me tell you the story. Some months ago I was learning Rust and I was like, okay, what can I do? I would like to write something. And I decided to write this SIP parser. I'm not a big VoIP guy, but I did it. And then I wrote the parser, and I was like again, okay, I want to know if this really works. And what I did is to set up an honeypot and collect attacks for 50 days. And this is the result. Here we can see the number of requests, SIP requests that I received. This is the number of the response sent by my honeypot. It is much higher than the number of the requests because when a specific SIP request is sent, the SIP server sends at least 2 responses. So no worries, it's not a bug, everything is okay. This is the number of unique attackers, so quite a lot. This counter is a bit surprising because when I was looking at traffic, I found out that some other SIP server were sending some traffic to my honeypot, which I think is a bit strange. This visualization is the number of SIP requests sent over time. For most of the time, it's a bit constant, except for this period where I really received a lot of requests. This visualization is about the top 15 talkers. You can see that some IP addresses, like these files, are most the same, so I think that they come from the same network, but I'm not sure. And also they send almost the same amount of requests. And we have a similar situation for these IP addresses. Maybe it's not really clear, but they are almost the same. The network seems the same. This visualization is about method. I will tell more later, but every SIP request has a method specified, and the most method sent is invite. Later we will see what invite means. This pie chart is about the number contacted, and here we can see that this value is the same to this, and to this. The only difference is the prefix, but it's a slight difference. This chart is about the status code and the reason phrase. This is a simple VoIP map. By looking at this map, I discovered that Victor from Netherlands have attacked my honeypot. No, sorry. Seriously, most of the attacks come from Netherlands, London, and USA maybe, or not. Okay. Anyway, this visualization is about most common user agents. Some of them are really strange, like this one, or this one. Instead, the most interesting are this Cisco SIP gateway, and we can see the asterisk user agent, which confirms what I saw before about the number of connections coming from other SIP servers. Then just some tables to show again what we already seen. So this is a list of methods. This is a list of the number contacted. You can see that these two numbers are the same. What changes is only the prefix. Same for this. And we have a table for status code and reason phrase. Just to wrap up with this part, I was quite surprising to see a lot of traffic and a lot of strange behaviors like this flow with the same port. Honestly, I didn't see any particular attack. These attackers were quietly, slowly in doing insane these attacks, so I was not able to detect any flooding or something like that. And most of them, what they did is to try to make some call without saying the authentication, which is a characteristic of the SIP protocol that we are going to see. And that's all for the visualizations. Now we can start with the slides. I'll give some context about VoIP networks. Then we will take a look about SIP from different point of view, like protocol characteristics, security problems, attacks, and stuff like that. Then I will introduce the Suricata SIP parser. And then if you want, we can take a look again at the visualizations. What is VoIP? VoIP is a group of technologies used for the delivery of voice and multimedia traffic over internet protocol networks, like the internet. It works like a phone service using the internet rather than the traditional telephone service, offering lesser rates as compared to many phone companies. The most common resources in a VoIP network are the user agent, which is an endpoint able to send and receive SIP messages and manage SIP session. The user agent client sends SIP requests, and the user agent server receives requests and returns a SIP response. This is to say that basically a SIP server acts like a server and a client because it receives SIP requests but also sends SIP messages. Proxy server is a component with UAC and US capabilities that function as an intermediary entity for the purpose of performing requests between other network elements. And a registrar is a SIP endpoint that provides a location service. It accepts the register request and records the address and other parameters from the user agent. This also is acted as a server because in general, a server must get the request from the clients, do registration stuff, and so on. But what is SIP? It's a signaling protocol used to manage a multimedia session. And a session is nothing but a simple call between two endpoints. It's defined in RFC 3251. And it can be used for two-party or multi-party session. But SIP is not an audio protocol, it's not a video protocol, it's not a data protocol. While it mostly applied to VoIP, it's not a VoIP protocol. So what's the role of SIP? What does SIP do? It tells you the presence of other party, makes a connection, and lets you do whatever you want over the connection, but it has no idea of what's going on over the connection. So it turns out that SIP is a media-independent protocol. And since SIP can't do the job by itself, it needs to work in conjunction with other protocols like real-time protocol, which is a specialized application layer for transporting audio and video when real-time streaming is needed. The RTP control protocol works alongside RTP to provide information about RTP packet delivery and manage the quality of the voice service. And the session description protocol works alongside SIP to specify which types of media the SIP client session can actually support. Let's take a look at some characteristics of the SIP. The protocol is based around request and response transaction like HTTP. And each transaction is made up of a request and at least one response. SIP messages are similar to HTTP and SMTP. It reuses most of the header fields, encoding rules, and status code of HTTP, and the URI syntax is similar to SMTP. A SIP request, like I said before, is made up of a method, a request URI, a version, and plus some headers. In SIP, 6 core methods are defined, like invite, which establishes a media session between the user agents, and a session is considered established if an invite has received a success response or an ACK has been sent. Previously, I said that when a SIP request contains an invite method, the SIP server sends 2 responses. Here in the picture, you can see this behavior. Basically, when an invite is sent, the SIP server at first sends the ringing response, and once that the call is accepted, the SIP response sends the OK response. So we have two responses for one request. The by method terminates an established session. It can be sent either by the caller or the callee to end a session. It cannot be sent by a proxy server, and it cannot be sent to a pending invite or an established session. Register performs the registration of a user agent. It's sent by a user agent to a registrar server, and it carries the address of record in the two header of the user that is being registered. A cancel is used to terminate a session which is not established, and it can be sent either by a user agent or a proxy server. Hack is used to acknowledge the final response to an invite request, and it always goes in the direction of invite. Option is used to query an user agent or a proxy about its capabilities, and a proxy never generates an option request. An URI is made up of a user, which is the identifier of a particular resource at the host being addressed, a password, an host, some URI parameters, and these parameters affects how the request is constructed, and also for the headers. Every SIP request or response must contain the version, which should be always SIP 2.0. The string actually is case insensitive, but implementation must sense the uppercase. Instead, a SIP response is defined as the SIP version, status code, a reason phrase, and some headers. Status code is a 3-digit integer result code that indicates the outcome of an attempt to understand and satisfy a request. The first digit defines the class of response, and the last 2 digits do not have any categorization role. For instance, the success category means that the action was successfully received, understood, and accepted. Instead, the reason phrase is intended to give a short textual description for the human user. Okay, let's go a bit deeper. What's the problem of the SIP protocol? Basically, the protocol itself is insecure by design because it is a text-based protocol, which means that messages are sent in clear and an attacker can collect, modify, and reply them. Integrity is not supported, so any modification and reply attacks are not detected, and the authentication often is not required, and this is specified in the RFC. And sometimes, if it's present, it is weak, because the basic authentication is used. This is a short list about most common attack for SIP protocol, like denial of services. Here, different methods can be used, like invite or register. Then extension enumeration, which means identify the live SIP extension. An extension is a client connected to a SIP server, and this attack basically is performed doing some brute forcing. Eavesdropping, which is the art of secretly listening to a VoIP conversation without the consent. Message tampering, which intercept and modify SIP messages. Registration hijacking, where an attacker impersonates a valid user agent to a register and replace the legitimate registration with his own address. And a session teardown occurs when an attacker observes the signaling for a call, which means that it intercepts the request and response, and then sends spoofed SIP by messages to the participating user agents. What we can do to make this protocol and our network safer? The most important thing, I think, is encrypt all the things, so all the communication. The SIP protocol and RTP have this variant called SIPs and SRTP, where permit to encrypt all the messages and the audio conversation using authentication with some strong form of authentication between SIP components, monitoring inbound and outbound SIP messages, looking for extension scanning, malformed messages, and malicious teardown requests, and plus monitor unusual calling pattern. Okay, we covered SIP attacks, countermeasure. Now let me introduce the Suricata SIP parser. It is available since Suricata 5.0. It's still disabled by default, but it works. It's written in Rust, and it works over UDP and 5060 port. Actually, SIP can work also on TCP, so maybe a good idea is to extend this parser to work for TCP also, a bit like DNS parser. I implemented also some basic logging where the request and the response are fully parsed and logged, but actually the headers are parsed but not logged, and also extended and custom logging is not implemented yet. I added some new buffers, sticky buffers for SIP also, like SIP method, where it matches on the method found in a SIP request. SIP URI, that matches on the URI found in a SIP request. Then SIP request line forces the whole SIP request line to be inspected, and the same for the response line. Stat code matches on the status code found in a SIP request, and the protocol matches the protocol field from a SIP request or response. Okay, let's take a look at some real rules that we can use to protect some SIP servers. If we want to detect some DOS attack, in particular invite and register, we can use the SIP method sticky buffer, looking for invite content and adding some threshold to keep track of the number of messages in a period of time. The invite flooding means that someone is trying to make too many calls. And instead, the register flooding means that someone is brute forcing the user connected to the server. And even for this flooding attack, we can use the zip method, but changing the content to register rather than invite. We can look also for 401 messages, because a high number of these messages means that, as I said before, someone is brute forcing the server. So we have two ways to detect these attacks. And here we can use the response line sticky buffer, looking for the string, basically the version, the 401 stat code, and the reason phrase. We can also use the state code sticky buffer and look for only 401 messages. Yes, SIP servers are also vulnerable to SQL injection because they can do authentication using some database. So a most common attack is to try and inject some SQL injection to delay it or trying to get this username and passwords. So here we can use request line and method request line sticky buffer and look for drop or delete or select, and also we can add some PCRE keywords. Okay, we already seen these charts, and that's all for me. If someone have any question, want to take a look again at the visualizations. Okay, thank you.
Thank you, Giuseppe.